Here in exercise 2, we're trying to prove that 3 to the 3n plus 1 is divisible by 7 for all positive odd integers n. So we'll take our proposition P of n to be the proposition that if n is an odd natural number, then 3 to the 3n plus 1 is divisible by 7. That's not obvious, so let's take a look and see at the first case and see that that's true. So we want to show that P of 1 is true, so we substitute 1 in for n. We see that 3 to the third plus 1 is 28. 28 is clearly divisible by 7. So P of 1 is true. Step 1 is complete. Now we're going to assume that it's true for some arbitrary value k. But here's the thing. We want n to be odd, so we're going to define k to be 2 times m minus 1, where m is a natural. And this is going to force k to be odd. So what we would have then is 3 to the 3k plus 1 must equal 7q. Now this is an important point here. So we've got 3 to the 3k plus 1, which I've defined k to be 2m minus 1. 3 to the 3k plus 1 is equal to 7q. We need to say mathematically that our expression is divisible by 7. And so how do we say divisible by 7 mathematically? Well, we realize that if a value is divisible by 7, then it's the product of 7 and some other number. We don't know what that other number is because we don't have a value for k. So we leave q to be a variable. And so we let q be some integer. I mean, really in this case, because k is a natural, q is actually going to be a natural as well, but for our purposes it's fine to leave that as an integer. But the key here is that we have defined this algebraically. 3 to the 3k plus 1 is equal to 7q. And that is how we are establishing divisibility by 7. You have to get good at that skill of expressing a definition in terms of symbols. That's what allows you to complete your proof. Okay, let's look at the third step where we show that given P of k is true, P of, in this case, k plus 2 must also be true. Let me pause here for a second because we said that in mathematical induction that the third step is such that when P of k is true, we show that P of k plus 1 must also be true. But in this case, because we're dealing with odd integers, we don't want to use k plus 1 because k plus 1 will be an even integer. So I'm using k plus 2, and that might seem like it's violating the definition of mathematical induction. And in some sense it sort of is, but what we want to realize is that we can just as easily frame this, and I set it up to frame it this way, that we could frame this problem in terms of m instead of k. And so, this m that we've created here that is part of the definition of k, we could use m to produce these, we could reword this slightly and make it such that we were proving things about m, and then this would be P of m and P of m plus 1, because when we add 1 to m, we're adding 2 to k. And so even though I have this written as a k plus 2, really, there's a corresponding proposition that is in terms of m, and such that when P of m is true, P of m plus 1 is also true, and that's really what we're looking at here, and it's an equivalent proof. So looking down at our steps here, we want to say that 3 to the 3 times the quantity k plus 2 plus 1 is divisible by 7. And again, since we haven't proven this, I have the question mark above to denote that we're looking to prove that. That's different than the equal sign here in the assumption step where we're assuming that this is actually equal. I do want you to notice right here one key point. I've talked about this before. Q and R, right? I've said for divisibility by 7 in this step, I'm using a different variable r, because 3 to the 3 times k plus 2 plus 1 is a different value than 3 to the 3k plus 1. And so if they're both divisible by 7, they'll both be multiples of 7, and they'll be different multiples of 7. So it would absolutely be inappropriate to reuse q in this case. And so we do need to define some new variable r, or whatever variable you'd like to use. So we're establishing divisibility by 7 again, this time with r, and we do some simplification. For some reason I wrote the same step twice, not sure what's going on there. But in any case, we've got 3 to the 6th now. What I'm doing is I'm separating out this 3 times 2, basically distributing 3k plus 6 and separating this 6 out so that again, I'm looking for the assumption step somewhere in my third step of the proof in mathematical induction. And so I'm trying to manufacture some piece of my assumption step so that I can do a substitution. And so hopefully this makes some sense. This 3 to the 6th is coming from this 3 times 2 and then times 3 to the 3k. You know that when you multiply, you add exponents. That's how we would get back to here. So I've got 3 to the 6th times 3 to the 3k plus 1 equals 7r. Now, here's a place where some people are tempted to do something that they shouldn't. People look at this and say, oh, 3 to the 3k plus 1. That's my assumption step. That's equal to 7q. So I'll just do a substitution in for this 3 to the 3k plus 1. I'll make that 7q, and I'm pretty much good to go because there'll be a factor of 7. You can't do that because of order of operations. Okay? Watch out for that. Big pet peeve of mine. You got to pay attention to order of operations here. This multiplication is happening before the addition, so we can't pull this expression out. We need to do something else. It looks like I'm going to have a really hard time separating this expression and doing a substitution for 7q. But there's nothing that says I have to use the assumption step directly as it's written. As a consequence of this assumption step, I know that 3 to the 3k is equal to 7q minus 1. All I have to do is subtract 1 from both sides of this equation. And that's the direct result of the assumption step. There's nothing wrong with I've said you got to watch out and make sure you only work on one side of the equation. I'm not proving anything about this equation. This equation is already true. I'm assuming it to be true. So I can do whatever I want to it, as long as it's legal. So I've subtracted 1 from both sides, and now we can certainly substitute 7q minus 1 in for 3 to the 3k. And when we do that, we get 3 to the 6th times the quantity 7q minus 1 plus 1 is equal to 7r. And again, we haven't proven this yet. We're trying to work on the left-hand side of our third step equation. And it is important to work on only one side of this equation because we don't know that it's true, and we're trying to assert that it is. So we're going to simplify the left-hand side here. I'm going to do a distribution. I'm going to simplify negative 3 to the 6th plus 1 and get minus 728. And I see that I've got two terms here, 3 to the 6th times 7q and 728. Now, 3 to the 6th times 7q, of course, is factorable by 7 as a multiple of 7 because I see the factor of 7 right there. 728, we can see, oh, that's also a multiple of 7. I can factor 7 out of 728. And I have two terms, each of which is factorable divisible by 7. So I can factor out the 7, and I see that indeed this left-hand side is a multiple of 7, and the right-hand side is as well. And so basically what we've done here is we've figured out the relationship between R and Q for this problem, and we've proven that this third P of K plus 2 is also true, and that this expression is divisible by 7. And so since the proposition is true for the first odd natural number, and the proposition is true for the next odd, when you know it's true for the current odd, it must be true for all odd natural numbers.